This is Saxon's Trig Lesson 6, Fractional Equations, Radical Equations, Systems of Three Linear Equations. So in Section A, it's fractional equations, and they jump straight into an example. So we've got 4/7 plus 3 over x plus 2 equals 5/3. In order to solve fractions, as we have talked about, we must have common denominators. And rather than keeping this problem in fractions, if I multiply the entire problem by the common denominator, I in essence can ignore the common denominator part. So for whole numbers, we have 7 and 3 making the common number 21. And then the x plus 2. So as we do when we are adjusting our fractions to common denominators, we say we have a 7 here, we want to put it to a 21, so this needs a times 3, and it needs the x plus 2. This one has the x plus 2, it needs the outer 21. This one has the 3, and it needs then the 7 and the x plus 2. I want to pause here and clarify something that I said. When I have fractions and I want to ignore the denominators to make solving simple, it must be in an actual equation with an equal sign in the problem. If it were just these two, you would have to keep the common denominator. You could not drop it. But when it's an equation with an equal sign, using the common denominator means I can drop it in this next step. So 4 times 3 is 12, and then the x plus 2, plus 3 times 21 should be 63, equals 5 times 7, 35, and the x plus 2. Then we need to distribute so we can continue to solve for the x. So 12 times x, 12 times 2, no change to the 63, 35 times x, and then that should be 70. Now I need like terms combined together. So if I moved the 35, I would end up getting a negative with my x. I'd like to avoid that. So let's minus the 12x when we move it, which means when I move the 70, I will definitely minus 70 to this side. So I know I'm keeping, oh wait, sorry, that's a 3, negative 20, oh, positive 23x, goodness gracious. Double checking that. All right, yes. Now, this is easier to do on a calculator, and I'm trying to do the calculations in my head. So 4, 5, 6, 7, 97 minus the 70, 27. And okay, I was checking my numbers here. Yeah, 23 I have correct. Oh, this is a 17. Did not subtract correctly. Double checking that. 8. There's my problem. 87 minus that makes more sense. 17. Okay, so then we divide by the 23. So x equals 17 divided by 23, and that is x's answer, and I box it. Okay, turning the page to page 50, we have example 2. Now this is a completely different problem than we just did a single one. This is giving me 2 problems. Oh, left my x off. Plus equals 11. And this one is 0.03x minus 0.2y equals negative 0.37. Now you'll notice that when I'm writing these out, just because I've done this so many times, it seems redundant to me to write the 0 over and over and over in front. As long as I don't lose the fact that these are decimals, I'm in good shape. If you prefer to keep the 0 there so that you don't have any sort of question, that is completely fine and is technically the more mathematical way to do it. All right, so since I have these 2 equations and it's asking me to solve them simultaneously, I first see that I've got this in fraction and this in decimal, and I don't want to work it in 2 different formats. So I'm going to fix them so that they are all whole numbers. So just like we did in the last problem, this one I can drop the denominator parts if I multiply by the common denominator, which would be 7 and 5 is 35. Okay, so now let's figure out the numerators. What am I missing to go from 7 to 35? I need a 5. What am I missing from the 5 to the 35? I need the 7. This implies a 1 underneath it, so it is missing the entire 35. So I need to multiply 35 times 11. I'm looking for, okay, that should be 385. All right, I'm just going to write that over here at the end, and now I'm going to go back and fix these and put them in front. So 3 times 5 is 15x plus, and 2 times 7 is 14y. Now I have it all in whole numbers. I want to do the same with these decimals, and so I look to see which piece has the most amount of places after the decimal. Well, this one has 2, this one has 1, this one has 2. 2 is the greatest amount. So I'm going to, in essence, multiply all of this by 100, or I'm basically moving all the decimals 2 places. So when I do that, I get 3x. Moving it 2 places here means that I'm actually filling in an extra hole with a 0 and my y, and then negative, moving it 2 places here, is straight up 37. Now I am ready to combine these two together with, and you can either, and I know we've not talked about either of these, eliminate or substitute. Substitution is typically the easier one. However, if I do that, because I've got 15, 14, 3, and 20, and none of them share a number, it's going to be I'm going to end up getting back to fractions to work with, which I was trying to avoid by going through this step in the first place. So I'm going to eliminate, and I need to choose. Am I eliminating the x's or the y's? And you should remember this from Algebra 2, even though we don't technically go over this lesson until later in the book. So 14 and 20 do not easily make a shared number, but 15 and 3 do. So I am going to choose to eliminate the x's, which means my common number will be 15. Since I want this to be eliminating the x's, I want it to be negative 15. So negative 5 times 3 will give me the negative 15. And of course, if I do that to one number, I need to do it to all of them. So down here, I'm just going to rewrite that first problem and then do this distribute. So negative 15x, negative 5 times negative 20 changes it to positive 100y, and then, again, I'm gonna have to look that up. Negative 37 times negative 5 is positive, and 37 times 5 is 185. And again, you should be checking this on your calculator to make sure that there are no errors. When I add these two equations together, I, in essence, eliminate those two. 14 plus 100 is going to give me 114y. 385 plus 185, 1734, so 570. And that does reduce evenly down to a 5. So I've solved for the y, but in the original problem, I have an x as well. So I can go back to any of the other equations that I wish to plug this 5 into. Using these is not super great because these numbers are large and I'd like to avoid large numbers if I could. On a calculator, it doesn't matter. I could go back to one of these, this one seeming to be fairly small, and I don't really want to go back to the originals because this one was in decimal and this one was in fractions. So I'm going to plug in here where I have 3x minus 20 times the 5, substituting that in, negative 37. 3x minus 100 equals negative 37. Moving this one over adds 100, so 3x equals, I'm trying to subtract this backwards. So 63, is that correct? Yes, and then divide by the 3, so x is 21. Now, because this was originally given in a problem where I had two equations with the x and y, it is implying that with that bracket around that original, that it wants the answer in xy coordinate format. And so always in a coordinate, the x goes first, followed by the y, and then I can box that answer. Radical equations in part B, they've got some dark words there, but basically you get what you need to know by going through the two examples. So in example 3, we have the cubed root of x minus 5 minus a2 equals 2. So anytime I'm dealing with a root radical kind of a problem, I need to get it isolated before I can undo the root. So we're going to first move this 2 over, which adds the 2. So I keep root x minus 5 equals 4. Now to eliminate the root, we undo it to its exponent format. So since this was cubed root, if I cube this, then they cancel each other off, just leaving the inside contents of x minus 5. And if I cube one side, I need to cube the other in order to keep everything in balance. So 4 cubed is 4 times 4 times 4, which is 64. And then move the 5 to add it. So x equals 69. And on a root problem, I do a quick mental check to make sure that the original, when I plug it back in, does not ever give me a negative, because if it did, it's an imaginary number inside a root and it would throw my answer off and would fall to the imaginary category, therefore not answered. But when I do 69 minus 5, that's clearly a positive, so no problem in boxing the answer. All right, example 4 has 2 square roots in it. The first one is s minus 48 plus radical s equals 8. Now the key here is, I said that when you have a radical, you want to isolate it, but this one has 2. Isolate the one that has more content inside it, which would be this one being longer. So we're going to keep it on this side and move this one over, doing its opposite, which means minus the root s. Now we eliminate this radical by squaring, and what I do to one side, I do to the other. So here I keep the contents on the inside. And this one, I purposely put a square root around it because I'm not squaring each individual piece. It is this concept, and again, I said in an earlier lesson that when you have a plus or minus, these things are stuck together as a unit. You cannot separate them into individual pieces. So this gets a parenthesis and is squared, which means I am doing this twice, and I'm doing the FOIL or distribute concept. So 8 times 8 is 64. 8 times negative root 3 is negative 8 root. Sorry, that's not 3s. Knew when I said it, it didn't sound right. And then I do the negative root s times 8, which is another minus 8 root s. Negative times negative is a positive, and radical s times radical s just keeps the s from the inside. Now we need to combine like terms before we can proceed. So this s and this s, no matter which way I move them, cancel each other off. And you want that to happen in every one of these kind of problems. The negative 48 and the 64, if I move it over, I make it minus 64. Negative 112 equals, and these two were like terms because they both had the radical s, negative and negative, so that will remain negative. 8 and 8 is 16 root s. Now we're going to isolate this root s to finish solving. So we divide by the negative 16. Negative divided by negative is a positive, and that is 7 equals radical s. And then we square both sides to cancel the radical. So s equals 7 squared at 49. Do a quick check. This one doesn't have any other numbers, so that's definitely a positive. 49 minus 48, that's a 1, so we're okay. So s equals 49.